Yes, it is exam week. So today's Monday, so you have an exam here this Wednesday. Chapters 1 and 2. We'll start bright and early at 7:20 if you can be here then. Coffee and or pop is okay, just don't spill. I used to once in a while have pop for breakfast, but I don't think it's a good idea. But if you want to. So we have extra time for it. The length is going to be about the same as old exams on Moodle, so if you think you can finish it earlier or quicker, you could come later if you want, but ideally, I'm going to be here by 7:20. Ideally, you are to start the exam. We will spend time reviewing today. That'll be our main thing. But I do want to do a new kind of example and talk a little bit more about limsups and lim-imps. And then kind of work backwards in our review. So we'll start with chapter 2 and work backwards to chapter 1 to remind ourselves of what we've done and what you should know for the test, what you should be able to do. It is no note card, no calculator, because for the main reason part of the test is definitions. And again, I don't really recommend making flashcards and sitting down and memorizing definitions, though if you feel like you need to, then go ahead and do that. What I recommend is studying it enough that you even could predict what the definition is supposed to be even if you forgot. Okay? You can figure it out based on the experience you've had. Is that a question, Travis?
Yeah. So, are we gonna need to be like brush up on our sine and cosine of things that aren't pi and pi over 2?
If you do need to know that, then I'll tell you. I haven't written the exam yet. What I do when I write the exam is I don't look at old exams. Okay, so I come at it new. At least for this class, some classes I use old problems, but for this class I come at it new each time. And what does that mean? It means definitely will be a different exam than old exams that are in Moodle. But you know, there's only so much that can be asked, although it feels like a lot. And there are certain things that are so important that I just can't really avoid putting them on the test. For example, state the completeness axiom. I don't think I can avoid having that be on the test. I don't want to avoid putting the definition of a limit of a sequence on the test. Those kinds of things, those two things I think are pretty much a guarantee of being on the test. So definition statements, theorem statements, maybe some calculation problems, true, false, multiple choice problems, and then some proofs. You know, some professors in this kind of class, the entire exam is proofs, but I like to make that just part of the exam. All right, so let's spend time doing one more kind of example that I want to show you. Actually, it's related to examples that we've looked at so far, but it's easier. I could see putting this kind of problem on the test. Define a sequence recursively by the equation, recursive equation, x sub n plus 1 equals, I'm going to make it nice and simple here, I'll make it a linear function, 1/2 x sub n plus 3. And also suppose the first term in the sequence, which I typically actually in this case call x sub 0, but I could call it x sub 1. x1 is 0. I could have called it x sub 0. You should be comfortable with either way. It's the starting term. It is actually common to call it x sub 0. What do we want to prove here? Prove that the sequence converges and find the limit. I could see a problem like this being a test problem that would be a proof. Or I could see it being a test problem saying, assume this converges and find the limit. We'll talk about how to actually find the limit after we prove that it does converge. But before we do the proof, it might be good to get a little feel for it by actually computing some of the terms in the sequence. Certainly should be able to do that even without a calculator here. So x1 is 0. x2 would be 1/2 times 0 plus 3. x3 would be 1/2 times 3 plus 3. 3 is 6/2, so we're going to get 9/2, 4.5. x4 will be 1/2 times 9/2 plus 3. 9/4 plus, what would be 12/4? 21/4. Let's do one more. x5 would be 1/2 times 21/4 plus 3. 21/8 plus 24/8, looks like it's 45/8. Look good to people? Okay, so it looks like it's an increasing sequence. Looks like it's monotone. 0, 3, 4.5, 5.25. What would that be? 5.5? Yeah. 5.5. No, 5.625, right? 5.625. Looks like it's increasing. When I say a sequence is monotone, and we're wondering about convergence, what's the first thing that should come to your mind, do you think? I heard somebody say something.
If it's bounded.
Is it bounded or not? And if it is, you know it converges. We got that monotone convergence theorem. A monotone sequence converges if and only if it's bounded. For sure it's going to be bounded below. Is it bounded above? Hard to say for sure. But I used to notice that each of these numbers is less than or equal to 6. Maybe it's bounded above by 6. I wonder. Maybe do a little scratch work over here. If xn itself is bounded above by 6, is xn plus 1 also bounded by 6? Bounded above by 6? If, you know, for the sake of induction, I assume this is bounded above by 6, it looks like that's going to do it. If you have to use induction, but it looks like that's going to be the case. Now, as far as if this were a proof on the exam, maybe I'd have to give you some help. Maybe I'd say, show it converges by showing it's monotone and bounded above by 6. Let's first show it's bounded above by 6 by induction. You could make that a claim. The sequence is bounded above by 6. And if I can also show it's monotone increasing, it'll also be bounded below by 0. Proofs within proofs here. Proof of claim. Proof of claim. It's okay to do proofs within proofs, I think. Use induction. Base case. N equals 1. X1 is 0. That's less than or equal to 6. Assume x sub n is less than or equal to 6. That's your inductive hypothesis. You can label it inductive hypothesis if you want. You don't have to. Then x sub n plus 1, we need to show that's less than or equal to 6. By the inductive hypothesis, this is less than or equal to 1/2 times 6 plus 6. Oops, made a mistake to them. 3. Which is 3 plus 3, which is 6. Therefore, the claim is proven by the principle of mathematical induction. It will be true. This will be true for all n. I really should say for some n here. If I didn't say that, I'd mark like a half a point or a point off my proof. For some n, how we're doing now seeing that. Therefore, xn is less than or equal to 6 for all n in the natural numbers by the principle of mathematical induction. The claim is proven. I could call that claim 1, I suppose. Claim 2 is it's going to be monotone increasing. If you don't like this claim style, you don't have to do it that way either. You can put this all together. Actually, we're going to see that this can actually be done without induction, which might seem strange. How can you prove something like this is true without induction? Because I'm going to show this is greater than or equal to 0 without ever using an inductive hypothesis. When you use induction, you're supposed to use the inductive hypothesis somewhere. This assumption back here with the proof of claim 1, that was the inductive hypothesis. I assumed it was true, and I needed that assumption to finish the proof, to prove it was true for x sub n plus 1. But here, it turns out you can do it without ever using an inductive hypothesis. Although, maybe I'm wrong. Let me think here. You can just replace x sub n plus 1 with its formula, 1/2 x sub n plus 3. Subtract x sub n. Simplify that to 3 minus 1/2 x sub n. I do need the fact that this sequence is bounded above by 6. I do need the truth of claim 1 to finish this proof. Because I want to show this is greater than or equal to 0. xn is less than or equal to 6 for all n. That will mean negative xn is greater than or equal to negative 6. And negative 1/2 xn is greater than or equal to negative 3. So this is greater than or equal to 3 minus 3 is 0. And that does it for an arbitrary n. I've shown that x sub n plus 1 minus x sub n is greater than or equal to 0, which means x sub n plus 1 is greater than or equal to x sub n. And yeah, I never used an inductive hypothesis. I did use truth of claim 1. So we've got a monotone increasing sequence that's bounded above by 6. It's also bounded below by 0, but you actually don't need that, even though the theorem is stated in terms of bounded sequences. Therefore, this converges. The truth of claim 1 and claim 2 imply that the sequence converges. QED or PTL, whatever you prefer. What does it converge to? Could it possibly converge to 6? Essentially, what you can do, once you know it converges, is you can take the limit of both sides of the recursive equation and use properties of limits really to write this. On the right-hand side, I used properties of limits, in particular the limit of a sum is the sum of the limits. The limit of a constant is the constant, and also constants can be pulled out. These equations are assuming all these limits exist. When taking the limit of the right-hand side, you can bring the 1/2 in front of the limit of that, And I have the limit of that, and that's a constant. Limits of constants are that constant. And even though I have a subscript of n plus 1 there and n there, these two limits are the same. And that should make intuitive sense. And you know the limit exists, so you can say this is definitely true. For the sake of clarity, you could give the limit a name. You could call it L. L equals 1/2 L plus 3. Solve for L. 1/2 L equals 3, so L equals 6. There we go. 6 is the limit. Word of caution here. If the example had been something like this, change the 1/2 to a 2. For certain starting values of x1, you can still get an increasing sequence. For example, let's see. If x1 is 0, I believe it's increasing, then x2 is 3, and x3 is 9. It's an increasing sequence, but it doesn't have a limit. It's a monotone sequence. If, for some reason, you thought this converged, you do this exact same limit calculation, and you get an answer. You'd say L equals 2L plus 3, negative L equals 3, L is negative 3. The limit is negative 3, but it doesn't converge. So even though you could do this kind of calculation similar to what we did there, it's meaningless in this example because the sequence doesn't converge. What this calculation would show is if it did converge, the limit would have to be negative 3. Actually, the only starting value of x1 that makes it converge is negative 3. And when your starting value is negative 3, you get negative 3 back out again. It's a constant sequence in that case. And that's actually the only starting value that makes it converge in this example. You can understand why with those cobweb plots, actually. Though in this case, they're really like staircases. Consider our first example here. If you graph 1/2 x plus 3, it's about like this. In addition to the line y equals x, it looks about like this. I'll try to make this match up good. And you start at 0, like we did. x1 is found by going up to the graph. If x1 is 0, then x2 is 3. To find x3, you can go over to the line y equals x before going back up to the graph of y equals 1/2 x plus 3. And the second coordinate of that point should have been 4.5, I believe. Yeah, that's x3. x4 can be found by going to the line y equals x and going up to the graph, and the second coordinate of that point is x4. And you're forced to head to where these intersect, and they're supposed to intersect at 6, which looks good down here, but doesn't look so good there. My scale is off here. Okay, that's supposed to be 6 there, even though I didn't draw it that way initially. On the other hand, with this new example, right there, draw the line y equals x, draw the line y equals 2x plus 3, it looks about like this. And now when you start at 0 and go up to that graph and go over, you keep going further away from where they intersect. You never head down toward negative 3 here. So that's a graphical reason why this one converged and this one didn't. You aren't going to have to know cobweb plots for the test. If you find them confusing, I know I've gone over them quickly for sake of time. You can look up information on the internet about it. Maybe I'll spend time explaining them more carefully sometime later. What about limsups and lim-infs? That was a difficult subject that we only introduced last time. Let's should you know about those for the test? So this could be a test kind of question here. Again, maybe with help. For example, saying, show it's bounded above by 6 would be the kind of help I'd give you. You should know the definition of a lim sup and a lim inf, and based on the definition, you should be able to think through, for simple examples, what the lim sup and lim inf are. Let's consider a lim sup. By the way, if a few of you go into grad school, sometimes people write lim sups differently. Sometimes they write lim with a bar over it. Lim sup. I don't know. It's just a notation you sometimes see. But our book, you can just stick with what our book does, and I will too. By definition, it's the limit as n goes to infinity of a sequence where this sequence is defined by a sup. It's written like that in the book. Might be easier to think about if you actually write the set out like this. For any given sequence, the lim sup is defined this way, although it could equal, quote unquote, infinity. It could be a divergent sequence here, these supremums that you get for each n. Could create a divergent sequence, though if it does diverge, it's got to diverge to infinity. So this is a limit in the extended sense. It actually can even diverge to minus infinity. So the lim sup can actually equal minus infinity too. But in the case, let's just imagine a bounded sequence. And let's imagine a couple examples. First, let's imagine one that bounces back and forth. And as it bounces back and forth, the terms are also getting closer together. But they're never really, the two sides, so to speak, are not approaching each other. So when I drew that, I was thinking of this as being x1, this is x2, this is x3, this is x4, x5, x6, etc. These terms, the odd index terms, are piling up, so to speak, near some number, say. Call it L1. And the even index terms are piling up near some other number, L2. What's the sup of x1, x2, x3, etc.? What's the least upper bound of the set of all the points in the sequence? It would be equal to x2. x2 would be the least upper bound of that as a set of points. What would be the sup of that set? So now we're deleting x1 from the set. x2 is still the least upper bound. This is going to mean x2 is going to be the lim sup. Let's see what happens with the next one. The next term in this sequence, when I say this sequence, I mean this whole thing, is the sup of this set. The sup of that set's no longer x2, it's x4. We've deleted x1 and x2 from the set. Set of outputs of the sequence. x4 is the least upper bound of this set. If we kept going, the next one, the sup of x4, x5, x6, etc., would still be x4. But then if we delete x4, if we consider the sup of x5, x6, x7, x8, then the sup is x6. So this sequence that we're generating by thinking about these sups consists of x2, x2, x4, x4, x6, x6, then it would be x8, x8, x10, x10, x12, x12, It would be these even indexed terms of the original sequence, where you count them twice each time, but it is a new sequence converging to L2. L2 would be the limsup of the sequence that I've just drawn visually. Would it be easy to make a formula for a sequence that looks like this? Yeah, not too hard. -1 to the n. What would it be? Maybe plus -1 to the n over n, maybe something like that. Let's see if I'm right. There would be the first term in that sequence, -2. The second term would be +3/2. The third term when n is 3 would be -1 minus 1/3, -4/3. Then you get 1 plus 1/4, 5/4. That would be a sequence that does kind of look like this. L1 would be -1 and L2 would be +1. The limsup would be +1. Go back to that, that theorem. The Cauchy book, it'd be good to open it up. The theorem that we really mostly focused on at the end of class last Friday, when I was discussing limsups and lim-imps. I wrote it on the board, I said this wasn't a definition, it was a theorem. We're talking about page 73. What did the theorem say? Given a bounded sequence, let S equal the set of all numbers that are limits of subsequences of that bounded sequence. The set of all possible subsequential limits. The limsup was the sup of that set. What's the set of all possible subsequential limits in this example? It's a two-element set, L1, L2. The sup of that set is L2. It's the limsup of the original sequence. It's a little easier to think about that than it is this. This is not too hard for specific examples. It's more difficult in the abstract to think about and prove things with it. Like the proof of all those properties in the book, which you should have read. Those are pretty tricky proofs, I think. I'll talk about what you need to know about those properties in a few minutes. But certainly you should know that the limsup of the sequence also, by a theorem, is the sup of the set of all possible subsequential limits. All numbers, all points that are limits of some subsequence of the original sequence. The two-element set in this example, take the larger one, that's the sup of that set, and that's the limsup of the sequence. Questions?
But wasn't x2 going to be the limsup?
No, the limsup's L2. x2 is the sup of this set, the sup of this set. x4 is the sup of that set. x4 would be the sup of the next one, then x6, then x6. That sequence that I'm generating is convergent to L2 by definition. Like the limit of that sequence, that's the limsup of the original sequence. Tricky. Yeah. Let's modify this example slightly. Let's say they pile up from the other side to two possible subsequential limits. Okay, x1 is here, x2 is there, x3 is here, x4 is here. I mean, the lim-inf, by the way, that other example would be L1. I hope that's clear too. That's x3, x5, x6, etc. Back and forth they go. The even index ones are piling up here near L2. The odd index ones are piling up near there, L1. By piling up, I really mean the limit of that subsequence, for example, is L1. Once again, you've got two numbers that are limits of subsequences. The sup is going to be L2. What if you use this approach, though? What if you use the definition? What would happen? In each one of these cases, no matter what n is, with this example, this sup would be L2. it would be a constant sequence, and its limit is that constant L2. L2 is the sup of the set of outputs of the sequence, no matter what n is. It's the sup of that set right there. So by definition, this is actually a trivial example. Things can get really complicated, though. I claim without proof that that sequence, its S, so to speak, its set of all points that are limits of subsequences, is the entire interval from -1 to 1, including -1 and 1. It fills the interval densely, say. And the sup of that set is 1, the limsup of the sequence is 1. It's a fact you should know on the exam. I could put that as a true-false question. I'm not going to ask you to prove it. It's very difficult to prove for an introductory class. Second here. You should know that fact. There's also that recursive sequence that we looked at that went all over the place. And you put a 4 here in this quadratic, and you start x0 or x1 to be between 0 and 1, like 0.1. You should know that S here is the entire interval from 0 to 1, and so the sup of S is 1, the lim sup of this sequence is 1, and the lim inf is 0.
What did you say the limsup was for the sign?
For this one?
The sign.
The sign?
Yep.
The lim sup is 1, the lim inf is -1. S, again, is the set of all numbers that are limits of some subsequence of this. It's the entire interval. There's uncountably many numbers there. There's uncountably many subsequences that you can make. It's the entire interval. The supremum of that interval is 1. That means the lim sup of the sequence is 1. The inf of that interval is -1. That means the lim inf of the sequence is -1.
So whenever you're saying limit, you're kind of pointing towards like convergence towards some number.
Whenever I'm saying,
In a sense, like for a certain sequence, or for, I guess if you were to say like a subsequence, so like the even positive numbers compared to the odd positive numbers for that, it'd be like what that subsequence is converging to.
what I'm saying is, I'm not quite sure what your question is, but what I'm trying to say is, as clearly as I can, is that for, take this sequence here. Give me any number between -1 and 1. I could take, square root of 17 over 5 or something. There's going to be some subsequence of this sequence that converges to this. Okay? In fact, there's going to be infinitely many subsequences that converge to it. Give me any number between -1 and 1. There's infinitely many subsequences that converge to that number. Crazy. Okay? But it's true. Here's another example to think about. You know the rationals are countable, right? We know the rationals are countable. That's a fact you should know. It could be a true-false question. Consider all the rationals between 0 and 1. Since they are countable, you can create a sequence that gives you every rational between 0 and 1. Every rational between 0 and 1 is somewhere in the sequence. You can do that because you know the set of rationals is countable. That sequence has got to be dense. It's got to fill up the interval from 0 to 1 densely. In fact, every number between 0 and 1, including all irrationals, is a possible limit of a subsequence of this. And actually, the proof of that's not too hard. I'm not going to prove it fully, but give me any number between 0 and 1, say it's right there. How do you create a subsequence of this one that converges to it? Whether this is rational or not, just first pick some rational number, say not equal to it. It could be rational, so you could pick it to be equal to it, but that's not the point. Some rational in there. It's got a certain distance to that. They're not equal. You know you can pick another rational between them. And also, not just between them, but say less than half the distance between them. We want to make sure it converges at this point too. Don't just pick any rational between them. Pick one that's also less than half the distance. Say you pick it right there. And again, to keep things simple, let's just pretend it's still not equal to the original number. Pick a rational, it's got to be in the sequence somewhere. Maybe the first one you picked was x1, but the next one you picked that was right there was maybe x sub 17. My mind's on 17 for some reason. The next rational to pick that comes from the sequence, make sure it's between these two, but also to make sure you get a sequence that converges to the given number, pick it to be less than half the distance between them. It's getting hard to draw. Maybe it's x sub 245 is the next term in the subsequence that satisfies that condition. You can continue that process and generate a subsequence that converges to any given number between 0 and 1.
Can you go over your definitions of of convergence and when you use divergence, since it's different in the book?
That diverges is only to infinity. That's different from the book. The convergence of a sequence is the same.
So only to infinity. Okay,
Yeah.
Gotcha.
The sup of the set is 1, the inf is 0. That means the lim sup of the sequence is 1 and lim inf is 0. Using the theorem. Feeling sleepy? Stay awake, maybe watch the video again after class. I try to get it posted as soon as possible. After you've gotten some coffee. What about these properties of lim sups and lim infs? Probably the most important property is if your sequence converges to begin with, then the lim sup and the lim inf will be equal, and they'll equal the limit of the sequence. That's probably the most important property. If that converges, then the lim sup of the sequence and the lim inf are equal, and they equal the limit, the ordinary limit. All subsequences have to pile up on the ordinary limit, so to speak. They have to converge to the same limit that the sequence does. That's probably the most basic and important fact to know out of this big list of facts on page 71 and 72. 9 facts listed there. Which means back when we were going to use the lim sup in chapter 6 with the ratio test, it means that the Cauchy version of the ratio test can be used whenever that limit exists. The limit of the ratio. We're talking about infinite series here. And looking at ratios like that. If that limit exists, you don't have to worry about lim sups, because the lim sup will be equal to the limit. It's probably the most important basic fact to know. What about these other facts?
Can you explain?
You can say that this limit exists if and only if these are equal. That's how it's stated. What were you going to say, Travis?
Can you quickly go over to why the lim sup is equal to lim inf again? Quickly, if it's converging to.
Yeah, I think I need to get on to other review here.
Okay.
Just, I'm glad you want to know, but
So we're just going to take it as fact.
we're taking it as fact at the moment because we don't have enough time to prove it. Are any of these other facts worth knowing? Yeah, they are worth knowing. For the exam, probably we don't have enough time to focus on them.
Where are you looking?
I'm looking at pages 71 and 72.
Which one is the one that says the sigma
There's no property that says it exactly like this. The closest one is D,
No.
that says the sequence converges if and only if these are equal. But it would also be true that it equals the limit. This would also be true. Okay, let's continue backwards here now, because we're running low on time. Also in this section was the Bolzano-Weierstrass Theorem. Okay, let's try to remember without looking at the book. I'm going to try to give you prompts to help you remember. So I'm mostly going to do things verbally here. Bolzano-Weierstrass. By the way, I had a mind fart last time. I called it maybe the BZ theorem, and I said, did you have a GZ theorem in algebraic structures? And you did actually in algebraic structures. This factor group, well, that's the center. Oh yeah, or something about that was called the GZ theorem. I was thinking BZ Bolzano has a B and a Z in it, but I should have called it BW for Bolzano-Weierstrass. I don't know. Bolzano-Weierstrass, what does it say? It says if you've got a sequence that's bounded in some closed interval, if it's bounded, you can say it is in some closed interval, it's going to have some subsequence that converges. Could be the original sequence. And if it is the original sequence, then all subsequences converge to the same thing. That's a fact. Could be some subsequence that's not the original sequence. And in fact, actually the book mentions if the original sequence does not converge, there are at least two subsequences that converge to two different numbers. S, in that case, has got to be at least a two-element set. But S can be uncountable as well. It's kind of crazy. You also should know what a subsequence is. Okay, there's this intuitive understanding. You just take some of the terms in the sequence in the same order to create a new sequence. Notationally, you write it like that, where P sub n is an increasing sequence of positive integers. For example, the prime numbers 2, 3, 5, 7, 11, 13, for example, or the evens or the odds. Or it could be some sort of random thing, x3, then x25, then x 2,316, then x 1,123,417 could be the next term in the subsequence you're making. You've got to keep going forever, though. This is a monotone increasing sequence of positive integers. It never stops. You should know what a subsequence is. You should be able to define a subsequence. Do you need to be able to prove Bolzano-Weierstrass? That's probably beyond the realm of an exam. The proof rests on the fact that key fact that every sequence of real numbers has a monotone subsequence, which is kind of a tricky proof. It's right above the Bolzano-Weierstrass theorem on page 70. And I think that's probably the trickiest proof we've had so far. I was going to have you prove that on the test. I'd have to help you more than 50% of the way, probably. So I'm probably not going to put that proof on the test, but you should still strive to understand it. Actually, this theorem on the previous page, 2.17 part B, is the quickest way to prove the sequence does not converge, if it does not converge. If a sequence has two subsequences that converge to two different things, then the original sequence can't converge. That's the quickest way to prove a sequence doesn't converge, if it's easy to see two subsequences that converge to two different things. Keep going back. The next section, the previous section was about Cauchy sequences. Well, okay, two big facts in this section. A monotone sequence converges if and only if it's bounded. You could also say a monotone increasing sequence converges if and only if it's bounded above. And a monotone decreasing sequence converges if and only if it's bounded below. You should be able to prove either of those two facts. The book proves the case of a monotone increasing sequence that's bounded above will converge to the sup of the set of outputs. On the test, I have done it in the past. You should be able to prove that for a monotone decreasing sequence, that's bounded below, it converges to the inf of the outputs of the sequence. Proof's not much different. Just need to make appropriate modifications to the book's proof. It's not a real hard proof. It used the completeness axiom and the definition of convergence to prove a fundamental fact. It's not super hard. It's definitely something that could show up in the test. Definition of a Cauchy sequence could show up on the test, and a proof that a certain sequence is Cauchy could show up on the test. Typical kinds of examples we consider are rational functions, where the top and the bottom are linear functions of n. 3n plus 5 over 2n minus 6. Should be able to prove that's Cauchy. Should also be able to prove with the definition of a limit in the previous section, 2.1, that it converges to 3 halves. Ratio of the coefficients to the highest power. And you should also know the Cauchy convergence criterion, that if you do show it's Cauchy, you can say it does converge, because it's a Cauchy sequence, by the Cauchy convergence criterion. Previous section is the definition of convergence and all the basic algebraic properties, as well as the fact that any convergence sequence is bounded. I mentioned that's a proof that could show up on the test. Show that if you've got a convergence sequence that it's bounded. It's a nice little proof. Use of the triangle inequality in a nice way. The squeeze theorem, should be able to use the squeeze theorem in a basic kind of example like you had in the homework that I just turned back to you. You should be able to prove the squeeze theorem. It's not too hard to prove. That's a proof that can show up on the test. The proof of the fact down at the bottom of that same page 57 is a bit too tricky, I think, for a test. If you've got a sequence in a closed interval, then if it converges to something in that interval. It's not a super hard proof, but it's just a bit tricky. For the algebraic properties, like the ones that I wrote on here but erased, should be able to prove those for the limit of a constant times an, assuming that the limit of the an's exists, is the constant times the limit. That was a homework problem to prove that. Could show up on the test. The limit of a sum is the sum of the limits assuming these limits exist. And you can write this. That's one I think we proved in class. Had a capital N1 that came from this one and an L1. Capital N2 and an L2, and I said let capital N be the max of capital N1 and N2. Capital N is the max of capital N1 and N2 that exists because you're assuming these sequences converge. Then little n being greater than or equal to capital N means little n is bigger than or equal to both of these. And it was an epsilon over 2 argument to get a nice epsilon up at the end, and the triangle inequality was needed. The limit of a product being a product of the limits is proved in the book. It's a trickier proof, but doable if I gave you some help, perhaps, some guidance. I think I won't put the quotient on. The limit of the quotient is the quotient of limits as long as those limits exist and as long as you're not divided by 0. I will not put a proof of that on the test. It's not on the book. And I didn't make it a homework problem either. There are these definitions of what it means for a sequence to be bounded. Monotone increasing, monotone decreasing. You should be able to state those. You should be able to create a definition. What would it mean for a sequence to be eventually monotone or eventually monotone increasing? I've written that down, but I've mentioned it a couple times. as something you should be able to create your own definition of that. That makes sense. Going back into chapter 1. This stuff is irrelevant up there. Continuing backwards here, the last section of chapter 1 was kind of something we didn't really focus on in class. Basic definitions, what does it mean for a function to be increasing or decreasing? Strictly increasing or strictly decreasing? What does it mean to have a local max or global max? I have the word global in there. The book doesn't put the word global in there. Instead of local, they use the word relative. There are important definitions in that section. I am still going to leave that section to you, but you are still responsible for the content, those definitions especially. Could be. Previous section to that, 1.4, was about cardinality. What does it mean for a set to be finite, infinite, countably infinite versus uncountable? I did the fun proofs in class. The book's proofs are not quite as fun. Right? We made that diagram with the spiraling. It was not really a rigorous proof. It was just meant to convince you. Believe it. Help you believe it. Cantor's diagonalization argument. Actually, the book's proof that the interval from 0 to 1 is uncountable is not that hard, really, as long as you know their lemmas that they use. It is an argument by contradiction. Assume you've got a 1-to-1 and onto mapping from the positive integers to the entire interval from 0 to 1 and try to get a contradiction. It's actually not that hard of a proof when you get down to it if you believe the lemmas that they use. Yep, page 34. Yep. I could see that maybe showing up on a test where I tell you, I would remind you what the lemmas are. Theorem I wrote down from that section was that a countable union of countable sets is a countable set. 3 uses of the word countable in there. You should understand what that says. A countable union means the number of sets that you are unioning. I'm not even sure if it's a word, unioning. The number of sets that you are unioning is a countable collection. It's a countable union. The sets themselves are countable sets. They can each be put in 1-to-1 correspondence with the positive integers. The resulting set, the union of all those, is also a countable set. Amazing. Book's proof is not too hard, but probably not something I'd put on the test. The rationals is a countably infinite set. You should know that, whereas the reals are uncountable. Continuing backwards, the previous section 1.3 was about this, the fundamental thing here that complete this axiom, sups and infs, of sets here, not sequences. We're talking about sups and infs of sets, bounded sets of real numbers. Sequences generate sets. For any sequence, you can consider its range, its image, its the set of all outputs. It generates sets, but they themselves are not sets. Functions. Although functions can be considered sets too, but you're not tested on that. Right? It was in that preliminaries handout. That is no longer a literal handout. The Archimedean property, use it all the time. Something that's intuitively basic, but if you only assume ordered field properties and don't assume the completeness property, you can't prove it. You need the completeness property if you take that approach to real numbers. The fact that between any two distinct real numbers there's irrational and irrational, no matter how close those are. And in fact, you can say infinitely many rationals and infinitely many irrationals. They're both dense, though somehow there's uncountably many irrationals and uncountably many rationals somehow. It's a mystery. It's where the definitions lead us. They lead us to these facts, even though we have a hard time comprehending them. Section 1.2 is a kind of a section mostly focused on the triangle inequality and some basic definitions. What are intervals, for example? You should know the formula for a geometric sum. It's something you should memorize. Maybe not for this test, but certainly by the time we get to exam 3, you're going to want to know it. If you need it on exam 1, maybe I'd probably give it to you. And then the first section was about the fact that the real numbers are an ordered field. The rationals are as well. Basic ordered field properties. There's infinitely many ordered fields, by the way. Remember these things from algebraic structures? Adjoin a root. Here we go. That's an ordered field. That's bigger than the rationals, but strictly a subset of the real numbers. We don't want to do root adjoining in here, do we? No. But I mean, I just want to let you know there's infinitely many ordered fields.
You might want to in complex analysis.
Oh, yeah. Okay, any other questions? Okay, get good sleep as well as studying hard. Make sure you're not staying up all night. See you on Wednesday.